Okay, so we've just finished talking about transformations of functions. So here's a graph of a function f, and the question that I want to look at today, the question that we refer to as the beast, is what do we do when we're presented with the absolute value of f of x? How do we handle that function? What do we do with it? And I think it's best to handle this first from a graphical perspective. Okay, so if we think about it, what's going to happen when you take the absolute value of something is that if that object is ever negative, the absolute value bars make it positive. So if I look at this graph here, I should notice that the y values start to become negative here at -2, and they stop being negative at +2. So all of these y values are going to be made positive by the absolute value bars. So the graph of absolute value of x is going to look like something over here. We'll notice that a portion of the graph of f was unaffected by the absolute value bars, and then a portion of it, the portion from -2 to 2, was reflected across the x-axis. Okay, this portion here that was negative in the original graph got reflected across the x-axis when we did the absolute value function. Okay, so what we really have here is two scenarios. Okay, so the absolute value of f of x becomes a piecewise function. Sometimes nothing occurred, right? Sometimes you just have the same thing as you do in the graph of f. Okay, when does that occur? That occurs when my function was greater than, and I'll put also equal to 0. Okay, if I'm 0 or positive, the absolute value bars have no effect on me. When my y values are negative, though, okay, so when f of x is less than 0, then my graph, my y values, right, get reflected across the x-axis. And the transformation that we saw is a reflection across the x-axis is the negation of the function f of x. So bottom line is an absolute value function will always become a piecewise function, and all that you have to do for the pieces is determine when is my function positive versus negative. If the function is positive, nothing occurs with the absolute values, and if the function is negative, then I must take the opposite of the y values, the opposite of the function values, to make them become positive. And that's all we have to do. What this means is we are in the world of sign charts once again. Let's do an example. Okay, so this function is an absolute value function. We call it the beast, and the goal is to get the beast out of the cage the absolute value bars. We want to be able to do our mathematics without absolute values in them. Okay, it's very hard to do calculus next year with absolute value functions. So here's what we know right away. We know that this function is either itself or it's the opposite of itself. It's our job to determine when. Okay, so when is it the opposite of itself? It's the opposite of itself when this expression inside the beast is less than 0, and it's equal to what's inside the beast when this expression is greater than or equal to 0. So what we need to do is make a sign chart. What goes on the sign chart? Well, the same things that went on the sign chart before. Numbers that have no sign in our expression, which are numbers that make it 0 or undefined. So let's determine what makes this 0. No numbers make it undefined, so I don't have to worry about that. This x minus 3 and x minus 2 is how that expression factors. So that means that this expression is equal to 0 if x equals 3 or if x equals 2. So we make a number line, and we partition the number line into 3 pieces, one that stops at 2, one that stops at 3, and then we do a sign test to determine what are the values of the function in these different subintervals. So if we use 0, for example, we'll get a negative times a negative. It's a positive. If we use 2.5, we'll get a negative times a positive, which is a negative. And if we use 10, we'll get a positive times a positive, which is a positive. So what does this mean for us? Okay, when is my expression inside the bars, the beast, positive? Well, from negative infinity to 2 and from 3 to infinity. Okay, so I can write that a couple ways here. I can write an interval notation, so I will. So it's x squared minus 5x plus 6 between negative infinity and 2, and I'll include the 2 because 0 has no sign and the absolute value of 0 is still 0. Okay, and from 3 to infinity. And when this expression x squared minus 5x plus 6 is negative, which is from 2 to 3, then I'll need the opposite of what's inside the bars. Now, if there's stuff outside the bars, then that stuff just comes down along for the ride, but what you need to analyze is what's inside the bars. Let's verify that this is correct on your TI Inspire. So what I'm going to do is graph the original function and then my piecewise function and show that they are the same. Okay, so I'm in the graphing screen, and the first thing I'm going to do is graph the absolute value of x squared minus 5x plus 6. So the absolute value bars will be found in the menu or in my template menu. So I see them right here. And so I'm going to enter in x squared minus 5x plus 6. Okay, and I see a graph that's produced. Okay, I'll go ahead and leave the label in there. I'm going to go ahead and take a screenshot of this. And now let me go ahead and delete that, and let's change the equation. And now it needs to become a piecewise function. So I again go to my template menu. Three pieces. And the first piece is going to be x squared minus 5x plus 6. And that's going to be when x is less than or equal to 2. We're going to use the opposite of x squared minus 5x plus 6 when x is between 2 and 3. So when 2 is less than or equal to, less than x and is less than 3. Okay, and I'll tell you right now there may be an issue with how I type this, so we'll find out in a second if the TI Inspire likes it or not. And then we got x squared minus 5x plus 6 if x is greater than or equal to 3. I don't always remember the order of symbols here, so let's see if it lets me do this. Okay, it does, and we see it in green. I'll move the equation over, and let's do a screenshot, and let's compare the two graphs. Okay, so I'm comparing the two graphs. They're in the same window, the same size, and I'm pretty convinced that they are the same. You could also graph them on the same screen together, and you should see them overlap. Okay, this is a good way to check your work and be confident that your answer is correct.